Hi students, welcome to VEDA Gate Academy. Now I can able to discuss FET and Mosfet. Okay, now I can able to examine the next chapter of the EDC, that is what you can call FET and Mosfet. So in the gate exam, this Mosfet can plays an important role. So it can carry more weightage in this gate exam. Now I can able to examine first FET. After that you can able to go for your required Mosfet. Okay. So first you can check out the field effective transistor, students. Field effective transistor, first you can discuss. This is called FET. So like a Bjt, FET is a body of 3-terminal device. It is a body of a 3-terminal device like a Bjt, you already know. So this FET is made by silicon, right? Bjt made by germanium or silicon, you know. So FET is made by what sir means silicon. Okay, and this field effective transistor is a unipolar device. Bjt is a bipolar device, you learn students, but FET is what sir means unipolar device. So in the case of field effective transistor, the current conductivity is purely by either electrons or holes. So only one type of carriers can participate in the conductivity, not both carriers, either 100% electrons or 100% holes we can call. So it is a unipolar device as compared to Bjt, that is a bipolar device. You know, this field effective transistor is a unipolar device, the current conductivity by either electrons or holes only. So in the case of field effective transistor, you do not find minority carrier effect, right? So it is a free from minority carrier effect you can call, and as compared to Bjt, field effective transistor is quite stable. Confirm my students? Okay, so Bjt is a bipolar device where the current conductivity by means of both electrons and holes, you know. As compared to Bjt, in the case of field effective transistor, what you find out means no minority carrier effect you can call. That is, field effective transistor is free from minority carrier effect, and it is look like to be quite stable than compared to Bjt. So this is one of the advantages of FET as compared to Bjt you can call. And one more thing, in the case of Bjt, noise effect is more. What is the noise? Noise is unwanted AC generated within active device under active condition, right? So understand the students, noise. So noise is a unwanted AC voltage generated within the active device under working condition, but under active condition of that body. So every active device can allow this internal noise up to certain extent, that is specified by the designer or manufacturer, that is called as a noise margin. Whenever the noise voltage cross the limit that is specified by the noise margin, what you can find out, sir, the output can have random changes irrespective of the input condition. So you are find out random changes at the output whenever the noise voltage cross its limit you can call, that is specified by noise margin. So in the case of Bjt, because of minority carrier effect is more, so noise effect is also high. So that you say that that is not be quite stable at the output you can call due to internal noise condition, the Bjt output may not be stable. But in the case of field effective transistor, what I told that the internal noise generation is very less as compared to Bjt, right? So as compared to Bjt, FET and as well as Mosfet are less noisy. Not only FET, Mosfet also the same thing. So the noise presence in the case of FET and Mosfet to be less as compared to Bjt. This is an advantage of that field effective transistor, right? And as compared to Bjt, FET size is small. Remember students? So as compared to Bjt, FET size is small you can call. Okay, and FET is a unipolar device you already know. And one more important thing, FET is a voltage control device. FET is what, sir? Voltage control device. You know Bjt, current control device. FET, voltage control device. What is the voltage control device means? In the case of field effective transistor as well as Mosfet, you know, any change in output current depend on input voltage. Any change in output current depend on or controlled by input voltage. So any changes in output current controlled or depending on what, sir, means input voltage. That is called as a voltage control device. By that, the field effective transistor to be named as what you can call, sir, means voltage controlled current source, students. FET and Mosfet are called voltage controlled current source. So BJT is a current controlled current source. FET is a voltage controlled current source. In the case of BJT, the output current change depend on input current you can call, but in FET as well as MOSFET, the output current change depend on input voltage, students. Okay, so look like a BJT. FET can also be used as a amplifier and a switching device. Amplifier and a switching device you can call. So here the output to be stable as compared to BJT I told. So it also look like to be act as an amplifier and a switching device. And as compared to BJT, the switching response is somewhat faster in FET. Okay, so it has somewhat a switching response faster than compared to what I told you, BJT. So you can find out so many advantages in FET as compared to BJT. But one of the main drawback of FET as compared to BJT is what, sir? In the case of FET, the gain is very, very poor. So the voltage gain, whatever that gain you have, so that is poor in the case of FET as well as MOSFET than compared to BJT. So you don't expect high gains like BJT amplifiers in FET and MOSFET. Why the gain is poor for FET as well as MOSFET means, so the gain depend on one of the parameter called transconductance you can call. So the transconductance value in FET and MOSFET is less, such that it have a poor gain, right, as compared to BJT as well as compared to BJT. This field effective transistor as well as MOSFET have what means poor gain you can call. Understand, students? So FET can be used as an amplifier as well as a switching device you can call. So many advantages you find out in FET as compared to BJT. So but only one drawback is there. As compared to BJT, the gain is less, I told, right? Simply you say that the gain bandwidth product is poor. What is the gain bandwidth product, sir? In any amplifier circuit, the overall performance will be indicated by the combination of vertical and horizontal elements. Vertical means gain, horizontal means frequency, that is called bandwidth. So the combined thing is called as a gain bandwidth product. So in the case of FET as well as MOSFET, the gain bandwidth product is poor than compared to BJT, students. Okay. And in the case of field effective transistor, you may find out that what means the current mechanism is main current mechanism is a drift mechanism. So in the case of BJT, the current mechanism, main current mechanism there, diffusion mechanism. So in FET as well as MOSFET, the current is mainly due to drift mechanism. Already in semiconductor physics, the drift current can able to flow as a function of applied electric field. So in the case of FET, right, the conductivity can be considered to be varied under the variational applied electric field. Under the variational applied electric field. By that, this person to be called as a field effective transistor. Here, which field is effective, sir? Electric field is effective. So it is a field effective transistor where the electric field is effective, indicating that here the main current mechanism is a drift mechanism. You know that the drift current can flow as a function of applied electric field. So the conductivity can be considered under the variation of applied electric field you can call. By that, here electric field is an effective one called as a field effective transistor. Understand, the students, what I told you? So FET is a 3-terminal device I call. It is a 3-terminal device made by silicon. Confirm now, students? It is a body of 3-terminal device made by what? Silicon. Right. As compared to BJT, I told you it is a unipolar device. It is a unipolar device. BJT is a bipolar device, students. FET and MOSFET both are unipolar device. What is the meaning of unipolar? Means only one type of carriers can participate in conductivity. That is conductivity by either electrons or holes, not by both. In BJT, the current conductivity by both electrons and holes you can call. Here conductivity by either electron or hole only, right? Not by both. So it is free from what, sir? Means minority carrier effect. It is free from minority carrier effect, students. So in the case of BJT, the minority carrier effect is more. For that you require that stabilization you can call. So that type of stabilization you don't consider in FET and MOSFET, students. So you already learned in BJT the minority current effect is more. So to keep that output to be independent of this minority current effect, you need that stabilization. So such type of stabilization techniques I don't want in FET and MOSFET because it is free from minority carrier effect you can call and is quite stable than compared to BJT. and is quite stable, students. Confirm. And once again you see this one now. I told that Bjt electrical behavior is similar to triode vacuum tube or triode valve I call. So FET electrical behavior or conduct electrical principle similar to what means pentode valve we can call pentode vacuum tube. Okay. So its behavior is nothing but what means same as to what pentode vacuum tube we can call. So triode Bz is nothing but what means. So triode vacuum tube we can say. Its electrical behavior is similar to pentode vacuum tube, students. Okay. So I told you it is less noisy than Bjt. So then compared to Bjt, it is less noisy. The internal noise presence is less in FET and Mosfet than compared to Bjt, you know. Again, I told that as compared to Bjt, FET size is small. And again, students, as compared to FET, Mosfet size again be small. Okay. Its size is small, I told. So now, its size is what? Small. And I told that it is a voltage control device, students. So FET and Mosfet both are voltage control devices. It is a voltage control device you can call. What is the meaning of voltage control device? I told you any change in output current controlled by input voltage, right? That is any change in output current. Any change in output current can be controlled. Understand the students? Can be controlled by input voltage. In Bjt, that can be controlled by input current, but here that can be controlled by input voltage. So called as what sir means. Based on this, it can be called as voltage controlled current source. Bjt is a current controlled current source, students. FET and Mosfet are voltage controlled current source you can call. Voltage controlled current source I told you, right? So the main current flow due to drift mechanism I told. The main current flow due to drift mechanism, students, such that here the electric field is effective to change the conductivity. By that I told that it is called as a field effect transistor. So the main current flow due to what? Drift mechanism, students. The main current flow due to drift mechanism, you know. And it can be used as an amplifier and a switching device, as I told you. Like a Bjt, it can be used as amplifier and switching device. And I told that as compared to Bjt, the switching response is fast. Okay. And it is a good amplifier as compared to Bjt. But the drawback of that one is what sir means. The gain is poor. That's a drawback as compared to Bjt. The drawback is that what is that one? Even it is a good amplifier, you don't expect high gain values in the case of a FET and Mosfet, because here the gain value mainly depend on one of the parameter that is called as a transconductance. That transconductance is less, such that this FET and Mosfet amplifier have poor gain as compared to Bjt. Okay. What I told you, the drawback is that its gain is poor. So you can able to check out later how it is. The drawback is that its gain is what sir means poor you can call. And as compared to Bjt, sir, the input impedance of that FET is high. So ideally the input impedance of this field effective transfer is infinite you can call, because input do not allow the current use ideally, but practically negligible current flows there. Based on that input impedance or input resistance of FET is very high, that is about 100 mega ohm, students. Okay. So what I told you, input impedance is high, that is called gate resistance that you can discuss. So this is about 100 mega ohm, students. So for ideal condition it is infinite, students. For ideal case, it is infinite. Okay, so it is infinite value for ideal case, and practically it should be high, about 100 mega ohms. You can call about 100 mega ohms. Understand the students? So now can able to check out first the family of field effective transistor, and one by one of that now I can able to examine the main things you remember as compared to Bjt. What means in the FET, you find out that that is a unipolar, free from minority carrier effect, quite stable, good amplifier. But only the drawback I told you, gain is poor. And other one is, as compared to Bjt, FET and Mosfet are voltage control device. And in Bjt, the main current flow due to diffusion mechanism. But in FET and Mosfet, the current flow mainly due to drift mechanism, you can call. Understand the students? Now, I can able to examine the family of this FET body. I can able to examine the family of this field effective transistor, students. This is that one now you can see. So it is mainly considered as a two. One is FET, that is also called as a JFET, students. FET or JFET both are same. Junction field effective transistor, JFET means. FET means simply you can call field effective transistor. JFET means junction field effective transistor. And one more family is what? Mosfet, metal oxide semiconductor field effective transistor. Metal oxide semiconductor field effective transistor, students. Okay. Now, metal oxide semiconductor field effective transistor, students. Now come back to the FET. Depending on the type of channel body you may use, depending on the type of channel body you can use, it can be classified as N channel. Other one is P channel, students. So depending on the type of channel body you are using, it can be classified as what? N channel and P channel you can call. So here also you can able to find out two type of things are there. One is depletion mode Mosfet, students. Depletion mode Mosfet. Okay. Other one is enhancement only mode Mosfet, students. Enhancement only mode Mosfet you can call. And each mode of this Mosfet again be classified depending on the channel body as two types, that is NMOS and PMOS. So N channel Mosfet, this is P channel Mosfet. Okay. Again, you find out two things, N channel Mosfet, P channel Mosfet. So this is the complete family of FET, students. Okay. So mainly classified as FET and Mosfet. FET again be two types, N channel and P channel, depending on the channel body. So Mosfet considered as two modes are there, depletion mode and enhancement only mode Mosfet, students. Here only the meaning is there that we can discuss later in that Mosfet. And each mode of Mosfet again be two types, so depending on the type of channel, NMOS and PMOS. And this Mosfet commonly considered the IC fabrication technique, students. And in this Mosfet, the most popular is enhancement only mode Mosfet, that is most popular to use in CMOS technology, and as well as is preferred in VLSI designs. I think that nowadays the electronic circuits are made by what means VLSI technology, making that electronic circuit as a microelectronic device you can call. Micro means reduced size of the body. So how it is means that is a rapid development in the semiconductor technology. That is now we are using VLSI. In that VLSI, CMOS can play important role, students. That CMOS is considered by enhancement only mode Mosfet. Okay, that you can able to examine later in the Mosfet circuits. Okay. So this is the complete family of field effective transistor. So in this condition, now I can able to go for first one, the FET. So what are the things you learn in the FET that is somewhat similar in Mosfet? For that purpose, first you can able to introduce to start the field effective transistor construction, working and VI characteristics. So what is the type of thing you learn here? Almost that should be comes to be similar in the case of Mosfet. For that purpose, so too easy to go through this Mosfet, first you can able to understand the field effective transistor. By that it is easy way to us to go the concepts of Mosfet. Okay, understand the students? First I can start this field effective transistor. So construction of a body. So one channel body I can take up, N channel suppose. What are the thing I told for N channel? The P channel also the same, just to the channel body is opposite. That you can discuss. Let us see this one now. Now I can able to check out the construction of this one, sir. Suppose I take an FET of N channel body I taken. So now I can take a body of a FET of n channel students. What is the construction? The construction is a simple look like a BZT you can call. So now a field effective transistor is obtained by taking what's that means. So this is an n channel body I told. So it is obtained by taking a lightly doped n-type semiconductor students. It is obtained by taking a lightly doped n-type semiconductor. So now I am doing. So I am taking a lightly doped n-type semiconductor of silicon. Why this person is a lightly doped one I can discuss later students. I take a silicon body of n-type material and which is lightly doped I can call. And so now students, I take a silicon bar of n-type material of lightly doped in the case of n channel. If you go for a p channel, the thing is nothing but p-type silicon bar of lightly doped you can take. Okay, so this is a silicon body of n-type material of lightly doped one for n channel FET students. So now what type of doped sir it is? Lightly doped I can call. Why it is lightly doped that I discussed to you later. Okay, so remember now students, look like a BZT. This person have 2 PN junctions. This person have how many PN junctions? 2 PN junctions. How to get the 2 PN junctions for this field effective transistor, sir? So look like a BZT, FET and Mosfet both have the 2 PN junctions you can call. How to get this 2 PN junctions, sir? On this n type of silicon body, on both sides at the center, I introduced to diffuse 2 highly doped p-type materials. And so now students, on this n-type silicon body at the center on both sides, I can able to diffuse highly doped p-type materials, highly doped p-type materials that are going to be diffused at the center on both sides. So see, so now this is one side, on that I can diffuse a highly doped p-type material, that is p plus. Like that also you can able to diffuse one more highly doped p-type material, that is called p plus. So I take a body of n-type silicon body, lightly doped one, over which a highly doped p-type materials, right, diffuse at the center on both sides you can call. Suppose if I go for p channel, here you can able to diffuse highly doped n plus materials. There you can take that body is n-type 1, likely to, there you can take it as a p-type 1 for p channel body. In the case of p channel body, you can take a lightly doped p-type silicon body on which there you can diffuse highly doped n plus materials. So it is n channel body, I diffuse highly doped p plus materials. Suppose it is a p channel body, you can able to diffuse highly doped n plus material students. Okay, so each p-type material with this n-type silicon body maintain a junction. So this is one p plus n junction. This is another p plus n junction students. Confirm? So each p-type material with this n-type silicon body maintain a junction such that this is a body of having 2 p plus n junction. This is one p plus n junction. This is another p plus n junction. So in the case of p channel FET, there we find out 2 p n plus junction students. There we can able to find out 2 p n plus junctions in p channel FET. Okay, in the case of p channel FET, you can take lightly doped p-type silicon body on which you can diffuse 2 highly doped n plus materials such that a p channel FET having 2 p n plus junctions. This person have 2 p plus n junctions. Confirm my option. And one more thing students, the space between the 2 p n junctions, the space between these 2 p n junctions should be called as a channel. The space between the 2 p n junctions should be called as what? Channel. The width of this channel is very important for conductivity. And remember that later in the working, the width of this channel can be controlled by input voltage such that output conductivity can be controlled. Based on that, you can call FET as a voltage control device. Understood my option? So the space between these 2 p n junctions I called as a channel. The width of the channel is important for conductivity, sir. The channel width can be mainly controlled by the input voltage that you can examine next. So based on that, output conductivity can be controlled by channel width controlled by input voltage. Based on that, FET called as a voltage control device. Confirm now? And it is a body of 3 terminals. I told students, how do you get that 3 terminals? Means 2 of the terminals are taken from opposite sides. 2 of the terminals are taken from opposite sides, students. And one more terminal can be taken from the 2 internally connected p-type material, students. So this is one p-type material. This is another p-type material. Both are internally connected. They are internally electrically connected, students. So from the two internally connected p-type materials, you can take one more terminal, students. So total it is a body of how many terminals you can call? So total it is a body of 3 terminals. It is a body of how many terminals? 3 terminals. So what are the terminals you taken from opposite sides? So those are called source and drain, students. Source. Other one is what? Drain. So middle one is what, sir? Means gate. So it is a body of 3 terminals I can call source, drain and gate. Now what are the functioning of this one also you can discuss. And so now, so the structure is very simple. It is obtained by taking a lightly doped n-type semiconductor of silicon body on which 2 p plus materials you diffuse to generate 2 p plus n junctions. Okay. The space between these 2 p n junctions would be called a channel. The width of the channel I told to be important, that you can examine next. So 2 of the terminals are taken from opposite sides of the body that are called source and drain, and the gate is an internally connected connection from 2 p plus material, students. Okay, so what is the functioning of this one also I can check out. If you go for p channel FET, A to Z is saying here you can use p type, here you can use 2 n plus materials. Okay, what are the thing I told you? So for n channel you say it has a lightly doped n-type silicon bar, students. N-type silicon bar. Sir, why it is lightly doped, that I can discuss to you later. Okay, for the time being you just remember it is a lightly doped. What is the purpose to keep that lightly doped? I can examine to you later in the working, students. Okay, it is a lightly doped n-type silicon bar on which 2 p plus materials you diffuse. P plus means highly doped p-type material, students. 2 p plus materials are diffused, means placed, we know, diffused at the center on both sides to have 2 p plus n junction, students. Confirm? So to maintain 2 p plus n junctions at the center on both sides are introduced to diffuse 2 p plus materials I call. I told you just now the space between 2 p n junctions is called channel. The space between 2 p plus n junctions is called channel, students. Is called, what do you say? Channel, through which the carriers can flow, that is can drift, through which the carriers can drift, students. So from one end to the other end the carriers can drift through the channel, students. Okay, and so now, so we have 3 terminals I can call, students. Those are source, drain and a gate. Source and drain are taken from the body of opposite sides and the gate is a middle terminal you can call. Now what is the functioning of this one I told students. Remember now, source is the terminal, through which the carriers can enter the channel. Source is the terminal through which the carriers can enter the channel body. So drain is quite opposite to source, students. Drain is quite opposite side to the source. So drain is the terminal through which carriers can left the channel. So it is the place of entry, it is the place of exit, students. What are the carriers who enter the channel body at a source? Must should exit at a drain. Now, source is the place where the carriers can enter the channel. Drain is the place where the carriers can left the channel, students. And source and drain always at opposite sides. And remember now, the functioning of source should be same as emitter function of Bjt. So there are some similarities between Bjt and FET terminal, students. So the Bjt emitter terminal is similar to what? Source terminal. In Bjt the carriers can be able to emit at emitter only. Here the carriers can enter the channel at source only. And what are the carriers who are emitted at emitter in Bjt? Exit or collected out at collector, which is at opposite side. In the case of FET as well as Mosfet, the carriers who enter the channel at source must should exit the channel at drain. Right, same thing. So source is same as to emitter, drain is same as to collector. That's the case. But remember, students, in the case of FET and Mosfet, the source and drain are interchangeable. Understood my option? So in FET as well as MOSFET, there is one of the flexibilities there. Source and drain are interchangeable, but you don't say emitter and collector are interchangeable. So in BJT, emitter and collector are not interchangeable, students, but in FET as well as MOSFET, source and drain are interchangeable. You understand what the meaning of interchangeable, students? Among the three terminals, middle one is always gate, students. Among these two extreme sides, what is that one? One of that one you can take as a source, automatically the other one can act as a drain. There is no restriction, this is source, that is a drain. So what are the two extreme terminals you can call? Among that you can accept any one of them as a source. Then automatically the opposite side terminal to act as a drain. Right? What are the terminal you adopt as a source through which the carriers can enter the channel? What are the terminal you taken as a drain? From that the carriers can left the channel. So that is called interchangeability. Confirm my option? So, but in BJT, it's not possible, students. So, emitter and collector not interchangeable there. But in FET as well as MOSFET, source and drain must be interchangeable among the three terminals. So, middle one is always gate you can call. What are these two extreme terminals, opposite terminals you can call? One you can take as a source, automatically the other one to act as a drain. So, what is the terminal you taken as a source through which the carriers can enter the channel? What is the terminal you taken as a drain? From there the carriers can left the channel. Confirm? And so is for now, students. What is this gate? Gate is a middle terminal you can call. Gate is a middle terminal, students. So this gate function is similar to base of a BJT. Why, sir? Means in the case of a BJT, base must be middle area, right? And it is of opposite impurity than compared to source and than compared to emitter and collector, you know. So in the case of BJT, base is a middle region and it is of opposite impurity than compared to emitter and collector. Here also same story. See this one now. Here, source and drain look like to be N-type, you know. Gate is a P-type. So, gate is a middle region of opposite impurity than compared to source and drain. Right? So, with respect to this gate of opposite impurity, you define two PN junctions in FET as well as MOSFET. Right? In the case of BJT also, because of the base is opposite impurity, you define two PN junctions. One is a collector emitter junction between emitter and base. Other one is a collector junction between collector and base. So in the same manner, in case of FET also, you find out two PN junctions by the gate of opposite impurity, which is at a middle area. What are the two PN junctions are? One is the input junction between gate and source. Another one is the output junction between gate and drain. Understand the students? So the similarities between FET and BJT terminals are source same as emitter, drain is same as collector, gate is same as base. Confirm? And this gate is commonly called as a controlled switch, students. Gate is called as a controlled switch you can call. Why do you call the gate as a controlled switch, sir? What are the voltage you applied at the gate? What are the voltage you applied at the gate? Can able to vary the width of the channel. By that, the drifting of carriers from source to drain to be controlled. By that, the conductivity can be controlled. Such that gate is called as a controlled switch you can call. Gate is called as a controlled switch. So, it is the connection taken from these two internally connected P-type materials, students. Two internally connected P-type materials you can call. It indicates two P plus N junctions you can call. One is a input junction between gate and source. Other one is a output junction between gate and drain. And gate is called as a controlled switch I can call. What is the voltage applied at the gate can able to vary the width of the channel and thereby controlling the drifting of carriers to get the conductivity of control. Okay. And so this one. So, how many terminals are there? Source, drain and gate. These things you know. Check out what I told you, students. Source and drain are at opposite sides, right? Source and drain are at opposite sides, students. Never be in the same side. At opposite sides you can call. The carriers can enter the channel, okay, at source. So the carrier can always enter the channel at where, sir? Source, and come out of the channel at a drain. Confirm? Come out of the channel to drain, students. What is this gate? Gate is a controlled switch I can call. Gate is a control switch, and the voltage applied at gate can vary the channel width, to get that variation of conductivity, students. Variation of conductivity, right? And I told you that gate is opposite impurity always. Gate is opposite impurity than compared to source and drain. Students. Drain and referent two PN junctions, So because of opposite impurity, that can define two PN junction, students. One is input junction. So here input junction is between what? Gate and source, and output junction between gate and drain, students. Output junction is between what? Gate and drain. And I told you now, in the case of FET as well as Mosfet, the source and drain are interchangeable, I told the students. Okay, that does not be possible in Bjt. Source and drain are always interchangeable. That can also be considered in Mosfet also, students. That not be happen in the Bjt, right? And I told that similarities are like this. The similarities between Bjt and FET terminals, right, are like this, I told that. So Bjt, FET, students. So in Bjt, the function of emitter should be same as the source of a FET, you can call. What is the emitter function? It is a similar, look like to be, what's the source of a FET? Here collector, that should be same, look like here as a drain. Here base, middle one of opposite impurity. Here that is the same, look like a gate, that is of opposite impurity, and it is the middle one. So these are the similarities between Bjt and FET terminal, students, right? And you remember here in the construction, you see source and drain are always the same as a channel type, students. Suppose it is N channel, source and drain are N type, and gate is always opposite to the channel type, students. So it is also be considered in Mosfet also, that you remember. Source and drain are always the same as a channel type. Gate is always opposite to the channel type, student. This is your standards. Okay, even in Mosfet also you can consider the same. Okay, in N channel FET, source and drain are N type, gate is a P type. Suppose if I go for P channel FET, students, there source and drain are P type and gate look like to be N type. That's the case. So remember now, source and drain are always the same as the channel type, and gate always opposite to the channel type. So in N channel FET, source and drain are N type, gate is P type. If I go for P channel FET, source and drain are P type and gate is N type, you can call. Remember my options, students? So what I told you, source and drain are same as channel type. What is the type of channel, you can call? Source and drain are also similar, but gate is opposite to the channel type. Gate is what? Opposite towards a channel type, students. Suppose if I go for N channel FET, if I go for what? N channel FET, so source and drain are N type, you can call. For N channel FET students. Source and drain are N type. Okay. So gate is opposite, you can call, that is gate is P type. Confirm? If I go for P channel FET, students, source and drain are P type. And gate is what, sir? N type you can call. This is the condition, students. Okay. And again you remember now, in N channel FET, the current carriers are 100% electrons only. In this one, the current conducted by electrons only, right? Current carriers are electrons only here. If I go for this P channel FET, students, the current carriers are holes only, you can call. Exactly here, holes here, electrons. So this is the case. Current carriers are holes only, students. So in the case of N channel FET, you discuss the conductivity by electrons. In P channel FET, the conductivity discussed by the drift of holes, students. So if I compare N channel FET and P channel FET, which is mostly preferred than compared to the other one, means I think that N channel should be preferred than compared to P channel FET. The main reason is in N channel body, the current carries electrons which have more mobility than compared to the holes of the P channel body. So who can able to causing a faster conductivity, sir? N channel body than compared to P channel body. So that N channel body have a good packing density over P channel body, such that which is mostly preferred, sir? N channel FET is superior or preferred than compared to P channel FET. Main reason is mobility of electrons is greater than mobility of holes, students. Okay, so my option. So which is mostly preferred there? N channel body is mostly preferred, right? N channel FET preferred over P channel FET. The main reason is this one, since the mobility of electron greater than mobility of holes. Since what are the reasons, students? Mobility of electron is greater than mobility of holes, such that mostly preferred is N channel FET as compared to P channel FET, you can call, right? And so now I can able to check out the symbolic representation of this FET, students. This is the symbol for FET. So I indicate that symbol for both N channel and P channel, students. Both the symbols look like the same with a small change. So this is suppose N channel I can call. So this is I call P channel, students. So it have three terminals, what are those are? Means gate, source and drain. Gate is a middle terminal. Okay. Source and drain are at opposite sides, This is the case. So if I see that symbol, both look at the same. And you remember the students, this long vertical line that can able to connecting the source and the drain, that to be called as a channel. So you have a conducting path between source and drain by the channel. So in FET as well as in depletion Mosfet, you can find out conducting path by the channel between source and drain. So I told in one of in that Mosfet family, enhancement only Mosfet, according to the construction, there is no conducting channel between source and drain. There in the case of enhancement only Mosfet, you can able to induce the channel, students. But in FET and as well as in depletion Mosfet, the conducting path is considered by the channel between source and drain. So that is a physical channel is present in JFET as well as in depletion Mosfet, students. But in enhancement only Mosfet, the physical channel not be present, that you can able to induce the channel with applied certain gate voltage. So this long vertical line to be called a channel, that indicate that there is a conducting path maintained by the channel between source and drain. Students. Sir, symbolic representation look like the same, right? Means the working nature of both N channel FET and P channel FET both are same, students. But how they can differ means in terms of the current flow. Because of the carriers are opposite, the current flows are opposite. Here conductivity by electrons I told, here conductivity by holes I can call. So principle is same, but current flows are opposite. Current flows are opposite, you can call. So here current mainly by electrons. How the current can consider, sir? By the flow of electrons from source to drain like this. Sir, whatever that may be, it is a N channel body or a P channel body, always the carriers can move from only from source to drain only. irrespective of the channel body of N-type or P-type. The N-type or P-type channel, what do you say means the conductivity is considered by the flow of carriers from source to drain only. See this one now. In the case of N-channel body, electrons are moving from source to drain, students. As the electrons are moving from source to drain means the current by the electrons in a direction opposite means the current coming towards drain to source. Drain to source means towards the channel. So this is the symbol. So the arrowhead and the gate terminal indicate conventional current flow direction, you can call. Suppose if I go for P channel, students, which can able to move from source to drain, sir, holes are moving like this. Holes are moving from source to drain. So what are the current by the holes in a direction similar to the holes, you can call. So holes are moving from source to drain means that holes current can able to move away from the channel, because holes are moving like this means the current is also in the same direction, you know. So that current can come out of the channel. So the thing of the symbol to be like this. The arrowhead is outward, here the arrowhead is inward, you can call. So N channel FET and P channel FET working nature is the same, just the current flows are opposite. Here the current flows are opposite. Why means here by electrons, here by holes. Anyhow, that arrowhead commonly indicate conventional current flow direction. Arrowhead commonly indicate what, sir? Conventional current flow direction, students. So this is the symbolic indication of N channel and P channel body. In terms of working nature, both are same, but the type of carriers are opposite, such that current flow indications are opposite. So in N channel body, the current flow towards the channel are indicated. In P channel body, the current flow outward from the channel are indicated. Here white is towards means by the electrons, white is outward means by the holes, you can call. Confirm now, students. And you already know which is mostly preferred over the other means N channel FET is preferred over the P channel FET. I told because the reason is mobility of electrons is greater than mobility of holes. Confirm now the students about the construction now. So remember now in FET as well as Mosfet, source and drain are always same as the channel type. Gate must be opposite to the channel type. That's a common thing you can call. Right? In N channel body, current by electrons. In P channel body, the current by holes. Okay. Check up now the working condition, current flow in this FET body, how it is. Now I can able to examine. Now I can able to go for students working of FET. So look like a BJT. FET can also be considered as a two-port network element, students. Look like a BJT. FET can be converted into two-port network element of 4 terminal, students, taking one terminal to be common to both input and output. So you know that BJT is a 3-terminal device. So by converting into a two-port network only can able to connect that BJT in the circuit design. You know, like that FET and Mosfet also have 3 terminals only. So they can also be converted into two-port network element by taking one terminal to be common to both input and output. So depending on the type of terminal you take and common in FET, you find out common gate, common source, common drain. So 3 type of things are there. Configurations, common gate configuration, common source configuration, common drain configurations. Right, look like common base, common emitter and common collector in BJT, in FET as well as Mosfet. You find out common gate, common source, common drain. But remember, students, right, FET as well as Mosfet mostly operating in common source mode. For right, being an amplifier, FET as well as Mosfet can able to find out to operate in what means common source mode, students. So for amplifying condition, the FET as well as Mosfet commonly operated in common source mode. So remember now the common source mode of a FET is nothing but same as common emitter mode of a BJT. Common emitter mode of a BJT. Confirm now, students. So now I convert the FET into a two-port network, taking one terminal common to both input and output, I told. So based on that I told common source, common gate, common drain. But preferably you can able to use common source mode of a FET, which is same as common emitter mode of a BJT, and common source mode is preferable to be used as an amplifier. What is that one, sir? You check up now. In the case of common source mode, what I told, sir, source to be taken common to both input and output, students. See this one now. This is the structure of that. So this is a N-channel body. Suppose I taken, students. This is a N-type silicon bar of lightly doped one, over which 2 P plus materials are diffused, you know. Each P-type material with that N-type semiconductor form a junction you discussed. The space between the 2 PN junctions is called as a channel, you know. Right, this is the source. This will be the drain. So gate to be taken from these 2 internally connected P-type materials. This is gate. This is the structure of N-channel FET you just now discussed, students. Now what I told you that in the case of FET as well as Mosfet, now one terminal taken to be common you can call. So which is mostly preferred to taken as a common means source to be taken as a common to both input and output, such that common source mode same as common emitter mode of a Bjt. So here input is made between gate and source, students, and output is made between drain and source. Input between gate and source and output between drain and source you can call. And so now this one, what I say? FET commonly operated in common source mode, students. CS means common source mode, which is same as CE mode, common emitter mode of Bjt. Okay, so input is between what, sir, means gate and source. Okay, and output is between what, sir? Source and drain. Output is between source and drain, students. Gate and source and drain. So yes, for now, students, the thing you remember now, what are the requirement here? Here the current carriers are electrons, I told. Now I need to make them to move or drift towards drain from source. I need to drift the electrons from source to drain. How to drift the electrons towards or drain from source, or means keeping drain to be positive with respect to source, students. That's a condition. In N-channel FET, who to be maintained positive with respect to the other means drain always at positive potential then compared to source. Thereby there is a easy drifting of electrons from source to drain. Suppose if I keep drain negative then compared to source, none of the electron can reach the drain. So conductivity is impossible. So for easy drifting of carriers from source to drain, in N-channel body, drain to be positive with respect to source. If it is a P-channel body, their current carriers are holes. For easy drifting of holes towards drain, their drain is negative, source is positive. Means source positive with respect to drain. So this is a standard even in Mosfet also, students. So in FET and Mosfet, these are the standard things. So in N-channel body, who can kept positive means drain kept positive with respect to source for easy drifting of electrons. If it is a P-channel body, there source to be positive with respect to drain for easy drifting of holes, students. Suppose here it is N-channel body. What the thing I can keep means I can able to maintain drain to be positive with respect to source. And this supply I can call as a drain supply. And the concerned voltage, terminal voltage, I can call drain to source voltage, simply called as a drain voltage. So one of that one I told you, right? And so now, students, in N-channel FET, what I told you, drain is at positive potential with respect to source for easy drifting of what, sir? Electrons towards a drain. Confirm? So for easy drifting of electrons towards a drain, what I told that, so which is made positive means drain is positive with respect to source, students. If it is a P-channel body, for P-channel, who is made positive? For P-channel, okay, source is positive with respect to drain, students. Source is positive with respect to drain. So S means the source, students. This means the source you can call. Source is positive with respect to drain. Source is positive with respect to drain. And so now this. Now again I can go for input condition, students. FET can operate in depletion only mode, students. FET can operate in depletion only mode. Remember now what is the depletion, what is the enhancement? Depletion stands for reverse bias operation, students. Enhancement stands for forward bias operation. So FET input condition is considered only in depletion mode, not in enhancement mode. Means the input gate to source terminal always kept at reverse bias, not in forward bias. Why it, sir, means I can discuss later. So FET can operate in what, sir? Only depletion mode. Depletion only mode you can call. That is with reverse bias gate voltage operation only, not with the forward bias gate voltage, sir. How it means I can able to confirm to you later, students. See this for now. FET can operate in what I told you? Depletion only mode. Depletion only mode means with a reverse bias gate voltage. What is that reverse bias gate voltage? Sir, gate is P type there, applied with the negative voltage. Source is a N type there, applied with the positive voltage. This one. This is negative, this is positive, students. This is called as a gate supply. Confirm my option. So FET operated in depletion only mode, students. Keeping reverse bias gate voltage operation means gate P type means negative potential apply, source N type means positive potential apply, and the corresponding terminal voltage is called as a VGS, gate to source voltage, VGS, students. Confirm now. So first of all, what the thing I can discuss, students, I can able to examine what the barrier effect, what is the effect on the channel by this VG gate supply and drain supply, I can discuss. So instead of making that both to be acting simultaneously, now I can able to make them to act separately means make them to act independent of others. So who can able to effectively control the channel width? For that, what will I do, sir? Means instead of making these two supplies to act simultaneously, I can able to make to present them independently. By that, I can able to confirm which of the bias supply causing a more effect on the channel, which of the bias can able to cause a more effect on the channel. For that, what will I say, sir? Instead of making to present them simultaneously, what will I do, sir? First, I can able to keep to present them independently. So in one case, one source is present, and the other case, other source is present. By that, I can able to identify what is the influence or effect of that concerned supply on the channel width. Okay, thereby can able to analyze the conduction of this body. Confirm my option, students. So FET operate in what mode? Depletion only mode. That is what, sir? Reverse bias gate voltage only. Is it right or not? Also I can discuss. And so now, students, so FET can operate in depletion only mode. I told. Check up now this. FET can be operated in depletion only mode, students. Depletion only mode, that is with reverse bias gate voltage VGS only. That is with reverse bias gate voltage VGS only, students. So FET can operate in depletion only mode. That is with what, sir? Reverse bias gate voltage only. Reverse bias gate voltage only, students. Okay. Now I can able to confirm now. First, I can able to examine what is the effect of each supply on the channel width. I can able to go and so this. See this one now. So two supplies are presenting, right? One at input, other one at output. Now instead of making to present them both at the same time, both are acting simultaneously. Instead of that, I can able to present them independent of each. So in one case, one source is presenting, in the other case, other source is presenting. By that, what is the effect on the channel by the supply, I can discuss. First, I can able to go with respect to gate voltage. Next, I can able to go with respect to drain voltage, students. See this one now. With respect to gate voltage, now I can discuss first. Keeping drain supply is open, students. This is N-channel material, right? Opposite are highly doped P-type materials, you know. This is a channel user. This will be the source. This will be the drain. This will be the gate. Confirm now, students. Now I can able to keep drain to source to be open. I don't apply anything, students, here. I keep this one as open. I keep that drain to source is open, students. I can apply the gate bias supply in between gate and source, you can call. So this one I can apply, students. This is negative, this is positive, you know. Gate supply I can call, and the corresponding is called gate voltage VGS. So with respect to VGS, I can discuss, students. See this one now. It is exactly reverse bias on the PN junction, you can call. On each PN junction, it acts as a reverse bias, students. So you know the fundamental condition of reverse bias. The reverse bias gate voltage, as the reverse bias voltage increases across PN junction, the barrier can expand. Simple logic, students. As the reverse bias voltage increases, the barrier that can be expanding across the junction. So this barrier can expanding on what side mostly, sir? What are the lightly doped area? The barrier can expand mostly. Confirm my option. towards highly doped one. So the barrier expansion is negligible even it is reverse bias, students. So the barrier expansion is commonly considered towards lightly doped area as compared to highly doped side. So if you compare this one PN junctions, P-type materials are highly doped one, then compare this N-type. N-type is a lightly doped material, So because of that, with the increase of this gate voltage, what are the barrier that can be formed across each junction? That be formed only in this lightly doped N-type channel place, not inside the P-type material of highly doped one. Because they are highly doped ones, sir, no expansion of the barrier in that P-type area. So the barrier should be expanding only in the lightly doped N-type channel, students. And it is an exact reverse bias you can call, so that you form a symmetric formation of the barrier. Like this, students, I indicated now. So this is N channel. So there the positive ions can be occupied. So this barrier can be formed across each junction, students, not only one junction. So across each junction, because gate is a common connection from two P-type materials, So this is the barrier formed across each junction, and it is an exact reverse bias, students. Not only one is one terminal reverse bias you can call. So exact reverse bias across each junction you can call. So based on that, the barrier effect across each junction is symmetric, and once again that can be found mainly into the channel. So now indicate as a shaded area, students. Suppose this is that one. Now we go. So this is the barrier. So that is occupied by positive ions because it is a body of N channel. So the barrier can be formed across each junction, and which must be symmetric. Which must be symmetric, students. Which must be symmetric across each junction because it is an exact reverse bias, right? And even for ordinary gate voltage, it can causing a more effect on the channel. Even for ordinary gate voltage, it can causing a more effect on the channel, students. So symmetric barrier effect I can call. Symmetric barrier effect with respect to gate voltage. And so now, for that reason, I can consider that N-type metal is a lightly doped one. Why I say this N-type silicon bar of lightly doped, sir, means the main reason I told you that. So for easy occupants of the barrier in this lightly doped channel, so that the channel width can be controlled by the occupants of the barrier, so that effective channel width come to decreasing on increasing of gate voltage. So it is an exact reverse bias I can call even for ordinary gate voltage. So the barrier can be occupied more space on the channel, so that the channel width is effectively controlled by this gate voltage, sir, and the formation of the barrier across each junction with respect to gate voltage must be symmetric. Confirm my option, students. So can I go for the other one with respect to drain voltage? How that one I can also check out. See this one now. With respect to drain voltage, I can go, students. This is the channel, N-type channel. Okay, of lightly doped one it is. These are P-type materials of highly doped one. Confirm. Channel body, students. Source. Drain. Source drain, This is the gate, students. So now I can keep that the gate to source is open, students. This is open, I can keep. I can apply a drain supply between a drain and source. So keeping drain positive with respect to source for N channel, So this is the drain supply. And a corresponding voltage, drain to source voltage called simply drain voltage. Now what is that drain supply or drain voltage effect on this channel I can able to discuss, students. With respect to drain voltage VDS we can discuss now. So with respect to the drain voltage you observe now, students, on the channel, what the thing you remember means. Okay, so towards the drain there is a reverse bias effect. So drain is at reverse bias potential with respect to source. So with respect to the drain voltage you find out there is a reverse bias effect at a drain as compared to source. So because of this, what are the barrier that by this drain voltage that could be expanding towards the drain only, not towards the source. So the barrier can expanding towards the drain, students, and while you come towards the channel of the source body, what you can call, sir, means the concerned barrier effect can get to tapered. Tapered means reduced. So there is a reduced effect as you move towards the source, and this barrier can expand mostly towards the drain only, because here you observe now this concerned supply keep that only drain to reverse bias potential with respect to source. So drain maintained at reverse bias potential with respect to source, such that the barrier should be expanding towards the drain and a tapered fall down as compared towards the channel body. So it look like unsymmetric barrier effect, students. See this one now like this across each junction. It look like a wedge shape. So it is expanding towards the drain, students, and while I come towards the source, that will be a reduced effect like this. This is the case. So here also same, students. So it is expanding towards the drain, and while you come towards the source, that will be reduced effect like this. Confirm? Suppose if I apply a ordinary drain voltage, no effect on the channel, students. For ordinary drain voltage, what is this barrier effect not causing effect on the channel? If I go for the drain voltage of higher values, that can causing a little bit effect on the channel. So if I compare both the drain and the gate voltage, so who can able to causing a more effect on the channel means gate voltage. Even you can apply ordinary gate voltage, it can causing effective, it can cause more barrier effect on the channel. So for ordinary drain voltage, here I told that the barrier effect is negligible, channel width is almost the same as the original. If I go for higher values, it can causing a little bit effect only. So if I compare both the drain and the gate voltages, who is a key person that can causing a more effect on the channel means gate voltage than compared to drain voltage. For ordinary drain voltages, what you can call, sir, no change in the channel width by the drain potential, because barrier effect is negligible, sir, like this. It's a unsymmetric formation, students, that I indicate as a shaded area now. This is the case. So the barrier is not be symmetric as I compared to the previous case. It should be unsymmetric, students. It should be unsymmetric, you can call. So this is unsymmetric barrier effect. So that should be what, sir? Unsymmetric barrier effect, students. So who is a person that can causing more effect on the channel width means gate voltage. For ordinary drain voltage, I told that so this barrier to be negligible such that channel width is same as original. Anyhow, what are the barrier that can expanding only towards the drain, students, has come towards the source, that will be negligible. So for ordinary drain voltage, no effect on the channel like all. For higher values of drain voltage, it can causing a little bit effect, that is ignored as compared to gate voltage. Confirm, students? And finally, you can confirm among the three terminals, gate, source and drain, with this concerned supplies, the barrier expansion is mostly towards where? Towards gate or towards source or towards drain means the barrier never expand towards gate, sir, because it is highly doped area. So other than that gate, remaining two terminals if we compare, so with respect drain and gate supply, the expansion of the barrier is mostly towards what, sir? Drain. So the barrier expansion in FET among the three terminals is mostly towards the drain, not towards the gate, sir, because it is highly doped, and towards the source is negligible, you can call. So mostly the barrier should be expanding towards drain among all the three terminals, you can call. Confirm, students? So I taken that individual effect. By that I confirm who is a key person that can effectively control the channel width by the occupants of the barrier means gate supply. Drain supply causing a little bit effect only. So the major effect considered by gate supply, and that too for ordinary drain voltage, no effect on the channel I can call. Such that what I can do, sir, I can able to represent the conductivity of the body. So by changing the gate voltage, because channel width is mainly controlled by gate voltage only, can call. So what will I do, sir, means I can able to control or vary the channel width by the gate voltage, and keeping this drain voltage to be fixed. Don't keep drain voltage 0, sir. If I keep drain voltage 0, no drifting of carriers. I must also need the drain potential. By that only drifting is possible. So instead of changing this drain voltage, I can keep that drain voltage to be constant. So keeping the drain potential constant, and now I can able to get the variation of conductivity by changing the gate voltage, students. By changing the gate voltage. So this is the barrier effect on each junction with respect to gate voltage and with respect to drain voltage. Confirm this, students? Okay, check out now. What I told you. With respect to VGS, right? Barrier effect is a symmetric. Barrier effect is a symmetric, you can call, and which can effectively control the channel width, students. Effectively control the channel width. Confirm. So with respect to VDS, I can go, students. With respect to VDS, drain voltage. With respect to VDS, drain voltage you can call. Barrier effect is unsymmetric, you can call. Barrier effect is unsymmetric. Barrier effect is what, sir? Unsymmetric, you can call. Okay, which is mostly expand what's sir? Towards drain. Expand mostly towards the drain, you can call. And tappers. Tappers means fall down, students. Reduced as move towards the source. So among all the three terminals, the barrier expansion is mostly towards the drain, students. And I told that for ordinary drain voltage, for ordinary values of EDS, no barrier effect on each channel you can call, right? No barrier effect on the channel body, right? So this one, for ordinary values of VDS, okay, the barrier effect is negligible. So the barrier effect is considerable somewhat by taking higher values of drain voltage. Under ordinary values of drain voltage, no barrier effect on each junction, students. Okay, so this is the condition you can call. Now you can able to analyze the working of FET with this one, keeping VDS constant and VGS should be variable, you can call, right? So understand now this one, we can examine the conductivity by varying VGS because it is effectively control the channel width, you can call. Keeping drain voltage is constant. So in FET and Mosfet, and the working nature to be considered by this case, students. So there in FET and Mosfet, what the thing you can do, sir, means commonly you can able to vary the gate voltage and keep the drain voltage constant. By that you can analyze the conductivity of the body. Okay, that I can able to examine now for FET, students. See this one now. This is the case I can discuss now. So this is your FET body, students. Body of N channel. Okay. So this is that one now. P-type material. This is one more P-type material. Channel body you can call. So this is a source. This would be a drain. This would be a gate, students. Got it now? Now what I told you that. So you can able to vary the gate voltage. This is the thing I can call. Reverse bias gate voltage, students, it is. VCC. To keep this one as a variable you can call. The corresponding is a gate voltage VGS. Keeping the drain voltage to be constant, students. In the FET of N channel, drain to be made positive with respect to source. So this is the drain supply, students. So this is VDS. I told that this could be kept fixed. Somewhere you can able to keep it fixed. You know that in this one, the current carriers are electrons, students. Current carriers are what? Electrons. See this one now, first case now I can able to go, students. First case now I can able to go. In first case, VGS equal to 0 I can call. I don't apply any gate voltage, students. Simply remember that gate to source junction is a shorted. So VGS equal to 0 means gate to source junction as what? Shorted I can call. So I can keep VGS equal to 0 volt, students, and I can fix this drain voltage VDS. So I can fix this drain voltage. So depending on the fixing of that drain voltage, there is a small barrier effect is there. But that barrier effect is negligible, students, because already know that for a ordinary values of drain voltage, no effect on the channel width I told. So this is that one I indicated. So with respect to the drain voltage, initially I don't keep any gate voltage, students. So gate voltage should be 0 I can call. So I can fix that drain voltage. So depending on that drain voltage you fix, there is a barrier effect, but that is a very negligible, students, like this. Negligible barrier effect you can call. So channel is almost same as the original. Right, channel width is almost same as the original with respect to drain voltage. Confirm my option, what I told that. Okay, keep VDS equal to constant, somewhere you can keep. Okay, at applied VGS equal to 0 volt. Applied VGS equal to 0 volt you can call. The barrier effect is negligible. Understood, students? The barrier effect is negligible you can call. The barrier effect is negligible, right? And channel width is almost same as original. So what are the original width as it is, it can be maintained. So channel width is almost same as what, sir? Original you can call. Understand the students? Now here current carriers are electrons. Here current carriers are electron, students. So I don't keep any gate voltage. Initially I told that this is 0 volt, students. I keep 0 volt already I told, nothing I apply. So current carriers are electrons. Depending on the potential you keep as a fix, this is a negative potential, students. So the negative potential can act as a repulsive force on these electrons. That negative potential can act as a repulsive force on the electrons. So channel width is free you can call. So because of this there is a tendency of maximum electrons can drift each time. Confirm my option. So there is a tendency of maximum number of electrons can drift each time, students. The number of electrons drifting each time is a large number. Why it is a large number, sir? Because channel width is almost free you can call. What do you find out, sir? Depending on the drain potential you applied. So with this negative potential there is a repulsive force is acting on the electrons, such that you may find out large number of electrons can able to drift each time and generating a current. So electrons are drifting like this means the flow of that electrons can define a current called drain current ID. And at VGS equal to 0 volt, students, at VGS equal to 0 volt, you see this one now, channel is almost free. The tendency of electrons drifting is a large quantity, such that drain current is maximum. That drain current is called as a saturated drain current you can call. That current is called as a saturated drain current, IDSS, students. Saturated drain current you can call. And originally it is the meaning of drain current under short circuit of gate to source junction. IDSS nothing but saturated drain current you can call. So it is also be considered as drain current under short circuit of gate to source junction, students. It is the highest current that can be defined under VGS equal to 0. Under VGS equal to what? 0. And remember now, commonly in any body, if I keep that input bias 0, no transfer current you can call. But in the case of FET, even the applied input bias voltage is 0. There you can able to find out the conductivity of output current. Now, even the input bias voltage 0, you can able to find out that output current. That is not ordinary again. That's a maximum value. Anyhow, whether it is ordinary or maximum, it's not the case. Even the input bias voltage 0, it have the ability to allow the output current you can call. By that, FET can be commonly called as a normally on device. So FET is commonly called as what, sir? Normally on device you can call. Confirm my option, students. Okay. So at VGS equal to 0, the number of electrons drifting, channel is a free means the number of electron drifting is a large quantity or small quantity. Large quantity you can call, right? As channel is a free, comma, at VGS equal to 0 volt, a large number of electrons can drift towards drain and generate drain current ID. Understand the students? Generate what, sir? Drain current ID can call. And I told you just now, At VGS equal to 0, number of electrons drifting is maximum. So drain current is maximum, we can call. Confirm now? At VGS equal to 0 volt, drain current is maximum, students. Okay. Called as saturated drain current. Saturated drain current IDSS, students. It is nothing but the drain current under the short circuit of gate to source junction, students. Under the short circuit of gate to source junction, you can also call. Got it now? Okay. And even the input voltage 0, it allows the conductivity such that it is called as a normally on device. Normally on device you can call. Confirm now? It is called as normally on device. Understand the students? It is called as normally on device because it can allow the conductivity. Confirm? It can allow the conductivity even if input VGS equal to 0 volt. By that, this fellow to be called as a normally on device, students. Normally on device. Okay. Check out the next one again. Sir, for VGS equal to 0 volt case, the maximum electrons are drifting because of channel is free. So that current is generated, drain current, that to be maximum, you can call. Now I can able to examine this one, sir, at a different values of VGS now. Suppose, now I can able to apply at a reverse bias of minus 1 volt, sir. It is already negative voltage. Here negative means reverse bias, sir. Reverse bias of 1 volt I apply. Reverse bias of 1 volt I apply. What happens, sir? The barrier can expand, sir. The barrier can able to expand now. Check up this, how the barrier to be expanding now. So this is the expansion of the barrier, students. So the barrier should be expanding by the applied gate voltage, previously 0. So no barrier by the gate voltage in the previous case. Now the barrier should be expanding. And that, you know, students, this barrier should be symmetric across each junction. This barrier should be symmetric across each junction, you can call like this. So what is that barrier previously that is negligible, you can call. But now, so because of this applied gate voltage, what do you find out, sir? Means there is a symmetric barrier effect across each junction. The effective channel width come to be reducing as compared to the previous case. Simply remember, students, in the previous case, each time I assume 1000 electrons are moving with respect to the applied drain voltage. And so now, at VGS equal to 0, just for a counter example, I assume that with respect to the drain voltage, keeping VGS equal to 0, channel is free, I told. Each time some 1000 electrons are moving from source to drain, so that my drain current, maximum current, you defined IDSS. Now I apply some reverse bias of 1 volt I applied at the gate. So barrier should be expanding on each junction. So effective channel width will be less as compared to the previous. So here, what is this? So drain potential is the same, not be changed one. So what is the repulsive force by this drain potential on electron is same. No change in the force also. So because of the drain potential is fixed one, the repulsive force by this drain potential on the electron should be same, not be altered. But as compared to the previous case, even the force is same, but as compared to the previous case, the number of electrons are drifting is now look like to be less than 1000. Why do you say less than 1000, sir? Previously this path is there. Now the path should be reduced, compressed. So even the same repulsive force is considered to be acting on the electrons by the drain potential. The number of electrons are drifting right from source to drain each time should be less as compared to VGS equal to 0 case. Suppose previously at VGS equal to 0 case, you told each time 1000 electrons are moving, but now that number to be less than 1000, suppose 800 like that. That's the case. Again I increase this one now, minus 2 volt like this, that is reverse bias of 2 volts, sir. Again the barrier can be expanding, sir. So increasing of reverse bias gate voltage, the continuous expansion of the barrier on each junction. Continuous expansion of the barrier on each junction, students, like this. Again the effective channel width again be decreasing again. So there is a again further decrease of channel width. So even the drain potential causing same repulsive force, but the number of electrons carrying each time from source to drain again be reducing. First VGS 0 I told 1000. Suppose VGS equal to minus 1 volt I told, at that time 800. Suppose minus 2 volt, it may become around 400 like this. So continuous increasing of this reverse bias gate voltage, there is an expansion of the barrier on each junction, thereby the effective channel width come to reducing gradually. Confirm now? so that the number of carriers are drifting each time to be continuously decreasing. So drain current continuously fall down below IDSS. So if you do this job continuously, students, at a particular reverse bias gate voltage, that particular reverse bias gate voltage is called as a cutoff gate voltage, students, VGS off. So this is a particular reverse bias gate voltage, students, that is called as a cutoff gate voltage, you can call. At that condition, the barrier of each junction is to touch each other. Confirm now? This is my original channel width at VGS 0. So as I increase the reverse bias VGS, sir, the channel width continuously decreasing, you can call, right? At a particular reverse bias VGS, I told you, the effective channel width come to 0 because the barriers of both sides are touch each other. So once the applied gate voltage is equal to VGS off, the channel width becomes 0. Once the channel width is 0, none of the electron can move from source to drain, students. What is the number of electrons move from source to drain means it's 0. No electron can move from source to drain. Then what are the drain currents are? 0. So where the body do not allow the conductivity. So body do not allow the conductivity means act as a off switch. Act as what, sir? Off switch. Understand the students? So this is the condition. So you confirm now the output conductivity can be controlled by changing the gate voltage. Output conductivity can be controlled by changing the gate voltage. By that, FET can be commonly called as a voltage control device. Confirm my option? See this one now? What I told you that? As reverse bias VGS increases, barrier expand on each side, then what I told you, channel width decreases. Confirm now, students. Channel width decreases means a drifting of carriers each time come to be reducing even the drain potential causing the same repulsive force, you know. So that ID decreases and fall below saturated current IDSS, students. Okay. So at VGS 0 current is IDSS. Now that current come down below IDSS, you can call. Confirm now? At a particular reverse bias VGS called cutoff gate voltage, students. Cutoff gate voltage VGS off, you can call. At a particular reverse bias gate voltage, students, called cutoff gate voltage VGS off. What do you say means? Both barriers are touch each other, I told. So that effective channel width is 0. Effective channel width is 0. Right? Both barriers are touching, sir, indicating that the channel width is 0, such that none of the carrier can drifting. Then drain current ID equal to 0, students. Then ID equal to 0, you can call, where FET act as off switch. Under switching mode, it can be considered as off switch, students. Correct now? So now, this is the controlling of output current conductivity to input gate voltage, students. So now next, sir, input gate junction is reverse bias. According to the PN junction of reverse bias, only minority current can flow. Ideally, FET body do not allow any minority current, sir. So for ideal condition, you say that here, whatever the gate currents are, for ideal condition, gate current should be 0. So this is the gate current, sir, that equal to be 0 for ideal case. Because input is exactly reverse bias. So in reverse bias, only minority current can flow. But you know that FET body do not allow the minority current. So for ideal condition, IZ equal to 0. Keeping input current 0, what you say, sir, means input resistance is infinite. Input resistance made between gate and source, that to be infinity, can call. Sir, practical case, if I go, a negligible minority current flow, sir, that is order of nanoamps, sir. order of fraction of nanoampere you can call. So because of negligible nanoampere of current flows across the input junction you can call. So input resistance is very high, that I told in the introduction is about 100 mega ohms. 100 mega ohms. So anyhow gate current is negligible, students, such that in a FET or Mosfet body you may find out only one current element, that to be called drain current. And you remember now, in the case of FET as well as Mosfet, drain currents will be same as source current, because I is equal to 0 you can call. Come on now, check out this. Okay, gate terminal do not allow current okay, because it is exactly reverse bias you can call, that is I is equal to 0, students, gate current equal to 0. So by that what I told you, input resistance who is made between input condition, input resistance Ri equal to input gate voltage by input gate current you can call. So Ri equal to VGS by IC, students. Ideal case, infinite, students. IC 0 means infinity can call. This is for ideal case. So it should be considered as a high value, students. That is about 100 mega ohms. Practical case. For what, sir? Practical case you can call. For practical case it should be what, sir, means. Okay, high value it is about 100 mega ohms you can call, because negligible gate current flows by the minority carriers you can call. So that is a fraction of nanoampere, students. Based on that will be very high. For practical case, ideally it is infinite. Sir, I told that FET to be operated in only depletion mode. It do not operate in enhancement mode. See this one now. Why it do not operate in enhancement mode? Suppose here I can keep that input is a forward bias gate voltage, students. Forward bias gate voltage means, see this one now, this is plus, this is minus if I apply. So I change the polarity of the supply, keeping gate positive with respect to source, look like a forward bias. So if I increasing this forward bias gate voltage, no change for barrier. Barrier do not be formed. So that no change in the channel width. That's over, student. And so now, suppose if I operate in enhancement mode, what are the problem I discussed to you? So keeping gate voltage positive with respect to source, what I told you, sir. So increasing of gate voltage, that is a forward bias voltage, no occupants of the barrier in the channel. So channel look let be free. But what my requirement? My requirement is to drift the electrons from source to drain, students. But here the problem is what? If I keep gate positive with respect to source instead of negative with respect to source, I told, what are the things, sir? What are the electrons here? What are the electrons here? Instead of reaching the drain, they can circulate between gate and source only, sir, like this. Because gate is a positive potential than compared to drain, so it is nearest to 1. So that instead of reaching the other end of drain, what are these electrons are? These electrons are circulating between gate and source only. They don't think about to move towards a drain. Such that the carriers that are drifting towards the drain is almost 0 there, such that the conductivity is not possible. That's the case. So if I operate in enhancement mode, what are the problems, sir? So channel is free, no problem, because barrier effect is not be considered in the forward bias gate voltage, you know. So what the problem here in this one means, instead of drifting the electrons from source to drain, what I told, sir, because of this gate made positive, so the electrons are able to circulating between gate and source, and without going towards the drain, conductivity is impossible. Such that FET body not operate in enhancement mode. FET body can operate in only depletion mode, students. Understand this condition? So FET is commonly operating in depletion mode only, I told. The main reason is that one. Why it is not operating the enhancement mode means, so under that condition, none of the carrier can move towards the drain. They are just circulating between gate and source, such that conductivity is not possible. Understand the students? So this is the working nature of field effective transistor. So finally you confirmed that any change in output drain current controlled by input gate voltage by the variation of the channel width of the barrier, by that FET can be called as a voltage control device. Okay. So check out the characteristics of this one again. So what I told you that, finally you can say that in FET, ID equal to IS, because gate current is 0. Okay, you told that output drain current ID, okay, can be controlled by input gate voltage VGS, and hence called as a voltage control device, students. And hence called as voltage control device. Confirm? So it do not operate in the enhancement mode I told. Why it do not operate in the enhancement mode means, under enhancement means forward bias gate voltage, no carrier can move towards a drain. So they can just circulate between gate and source, so that conductivity not possible I can call. Right, such that FET always operated in depletion only mode. Okay. Check out the characteristics of this FET students. See this one up. VA characteristics of FET students. So you know that in Bjt you find out input and output characteristics, but here somewhat different students. Input characteristics you don't define in the case of FET as well as Mosfet, because input gate current 0, so that it's not possible to you to draw that input characteristic graph, students. So it have output characteristic graph like a Bjt. Other than that, it can have a transfer characteristics to know that how it look like a voltage control. So FET have a two type of characteristics as well as Mosfet also. So what are the two characteristics are? One is output characteristics, other one is a transfer characteristics. You don't have input characteristics, sir, because it do not define the input gate current there, so that input characteristics are not possible. So it have output or drain characteristics as well as the transfer characteristics you can call. So transfer characteristics are nothing but define how it look like a voltage control. Okay, check out now. One of the characteristics, what's sir? Output characteristics. This is also called as a drain characteristics. So one of that one, sir. Output VA characteristics or drain characteristics you can call. So one more is what sir means transfer characteristics. So these are the two type of characteristics that you can able to find out for a FET students. Output or drain characteristics. Other one is transfer characteristics you can call. First of that one I can able to go to discuss, students. That is output of VA characteristics or drain characteristics you can call. Okay. First of that one I can discuss. Output or drain characteristics, students. How to define this output or drain characteristics, students? It is the relation between output drain voltage VDS and output drain current ID. Output drain voltage VDS and output drain current ID at input VGS equal to 0 volt, students. Sorry, at input VGS equal to constant, students. At input VGS equal to constant. See, it's not your working principle. According to the working nature, you know that keeping drain voltage constant, you are discussing how the output current varies with respect to gate voltage. So that you can examine the transfer characteristics. So it's not your working nature, sir. So according to the working nature, you are keeping drain voltage constant and discussing the conductivity with the gate voltage. That you can examine in the next characteristic graph called transfer. So this is output characteristic, students. Relation between output voltage of drain and output drain current, keeping VGS equal to constant. So what is the necessity to draw the output characteristics? One, mandatory to know the output impedance while I can use in amplifier. So using this, I can calculate that output drain resistance. One more. So differentiate the operating modes. You know that look like a BZ, it can act as a switching device and amplifier, you know. So where it look like an amplifier, where it act as a switching device, that can be analyzed with the help of this drain characteristics. That can be analyzed with the help of what? Drain characteristics, students. So now I draw that graph. See this one now. So this is the drain voltage VDS. Okay. This will be the drain current ID, which is about milliampere, students, keeping VGS equal to constant. So first one of the graph I can make, suppose for VGS equal to 0 volt case, students. For VGS equal to 0 volt case, I draw a graph and that I can analyze how it comes. See this one now? This is the graph I made for VGS equal to 0 volt case, students. VGS equal to constant I can call, VGS equal to 0 volt case I can call. See this one now, if I go to this graph, students, up to certain portion, the drain current varies linearly with the drain voltage, this one. So this is the portion I can indicate it, students. So in this region, the drain current varies linearly with the drain voltage. This is called linear or triode or ohmic region you can call. Confirm now? So, firstly, you remember now the drain current varies linearly with the drain voltage, students. Here, this one can be considered for ordinary drain voltage, students. So, what is that ordinary drain voltage? That is considered for linear condition. You check up now. So, for ordinary drain voltage, right, in the lower values of VDS, what I told, sir, as VDS increasing, the corresponding drain current increases linearly. Why it is, sir? Check up this option. So, this one now. I keep VGS equal to 0 volt constant, sir. VDS I can changing from 0. If I keep VDS 0, no force, no electron can move. So under VGS 0, channel is free, students. Leave that. Okay, VDS 0 means, so no force on that one. Electrons are 0 flowing, such that current is 0. Or if I make that, suppose 1 volt I can keep, students. So 0.1 volt I can keep, suppose 100 electrons are moving. Suppose if I keep 0.2 volts means, so force increasing, the linear movement also increases. So electrons movement also increases linearly, you can call. So 0.2 means 200, 0.3 means 300, like that. So under low values of VDS, as VDS increasing, so the flow of electrons increasing linearly because channel is free. So the increasing of potential of VDS under low voltage region, there is a increase of flow of electrons in the linear mode, and thereby the drain current can increase linearly. Right, the drain current can increase linearly, students. So increasing of the drain potential under low voltage region, what I can call, sir, means the repulsive force acting on the electrons also increases linearly, such that the current increases linearly, and thereby the current increasing like this. Confirm now? At a particular drain voltage, that I can call as a pinch off voltage VP. At a particular drain voltage, that I can call as a pinch off voltage VP, students. Pinch off drain voltage VP. The concerned drain current may attain its highest value. The corresponding drain current attains its highest value, sir. That to be called as a IDSS. That to be called what, sir? IDSS, saturated drain current you can call. So saturated drain current that I can expect it for VGS equal to 0. It is the maximum drain current, right? It is the maximum drain current, right? At VGS equal to 0 you can define. So now what is this pinch off voltage you define, sir? It is the minimum drain voltage. It is the minimum drain voltage at which the drain current become maximum and constant. Sir, why I say minimum drain voltage means after which also no change in current you say. So it is the initial value of drain voltage or minimum value of drain voltage where the drain current converted to be as a maximum and constant. That to be called as a pinch off drain voltage, students. Karpana? And so this is the other region, students, that you can call pinch off region. Pinch off region, it is also called as a saturation region. Pinch off or saturation region, students. See, so now, if you go for this pinch off or saturation region, that comes above pinch off voltage, where the curves have a flat response. Means the drain current remains the same, even the drain voltage changing. Why, sir? Already drain current reaches maximum, right? That is happen at pinch off point. So after which even you change the voltage, no further increase in drain current. Means that the drain current remain constant even if the drain voltage changing. Having a flat response, look like act as an ideal current source. Look like act as what? Ideal current source, students. Look like to be act as an ideal current source. This is the case. So linear region, that is nothing but triode or ohmic region considered for ordinary values of drain voltage, where the channel width is free, you can call. So what I told here, so in this region, so with increase of drain voltage, there is a linear movement of flow of carriers from source to drain. Thereby the drain current increases linearly and attains its maximum called IDSS at a particular voltage called pinch off voltage. After which you can enter a pinch off or saturation region. Right there, even the drain voltage changing, no further increase in drain current because already drain current attains its maximum pinch off point. So even the drain voltage changing, the current corresponding current remain constant, sir. So look like a flat response, act as a ideal current source there. Now, sir, I repeat this graph for another constant value of VGS, students. For another constant value of VGS, now I can able to repeat this one now. This is the graph you may get. VGS equal to -1 volt constant. So the height of that graph reduces. Why, sir? Means because of applied reverse bias voltage, some constant value of some non-zero volt you apply, automatically channel width is somewhat reduced one. So previously maximum number of electrons to be carried is nothing but suppose 1000 you can call, here maximum to be around 800 only. After that no further change in the flow of electrons. such that the drain current remain constant. So height to be reducing. If I do this job continuously, students, for another gate voltage, see this one now. If I take one more gate voltage, students, what happened there? See this one now. Like this. VGS equal to minus 2 volt. So increasing of that reverse bias gate voltage, the height come to reducing because channel width decreases, you can call. Right? And at VGS equal to VGS of, already know, sir. At VGS equal to VGS of, channel width is 0. So that drain current is 0 like this. This is that one, students. This is called VGS equal to VGS of. Cutoff gate voltage. VGS equal to VGS of, the drain current becomes 0 there. Because channel width is come 0, sir. Because of the barriers, both sides are touch each other, you can call. And remember, students, in this linear or triode region, you can call, or ohmic region, where the corresponding current changing linearly with the voltage, in this region, FET can act as a voltage variable resistor. In this linear region, FET can able to act as a voltage variable resistor, resistive body, and in this region, the FET can also be called as an on switch, varying of current linearly with the voltage. So switching application, on switch, and VGS off, look like to be off switch, you know. It is the off switch, students. And in these two regions, between on condition and off condition, this is the saturation region, you can call nothing but pinch off region, where it look like an ideal current source. And in this region, the FET body can able to act as an amplifier. Sir, FET or Mosfet can able to act as a voltage amplifier, sir, not current amplifier. Why, sir? Means, so input current not defined, so that you do not expect the current gain here, you are expecting the voltage gain. So probably it can consider as a voltage amplifier. So in this pinch off or saturation region, not only an ideal current source, it look like to act as an amplifier, look like to be mainly as a voltage amplifier, students. So this will be the VA characteristic graph of this. So in this amplifying area, taking a slope, you can able to get that output drain resistance. Output drain resistance. Understood, the students? So this will be the output VA characteristics you can call. Confirm? And in terms of the magnitude, you remember now. So pinch off voltage, pinch off drain voltage, and cutoff gate voltage both are same. Understood this? So what I told this one now, sir. So linear region, nothing but possible for ordinary drain voltage are close to 0 values of VDS, you can call, right? For small values of VDS, it has linear region, students, where ID increase linearly with VDS, linearly with the VDS, used as voltage variable resistor. VVR means voltage variable resistor, sir, and also as on switch. Okay. So what is this VP, sir? Pinch off drain voltage, you can call. It is the minimum drain voltage at which the drain current is maximum and constant, right? Pinch off drain voltage, students, VP can call, is the minimum drain voltage, at which ID become maximum and constant. So drain current become maximum and constant, students. Means there you can find out highest number of carriers are drifting, after which no further change. So that drain current remains constant. That is called as a pinch off drain voltage, students. So this pinch off drain voltage depending on what factor, students. So derived formula I am indicating, suppose here. So this is the formula for pinch off drain voltage, students. VP equal to Q ND A square by 2 epsilon. This is for N channel, students. Now I can consider the formula for pinch off drain voltage. So if I go for P channel, students, same thing. Channel body is different. So Q NA A square by 2 epsilon, students, for P channel. So what are these terms, sir? Q is reference charge. ND or NA considered for the doping concentration of channel. So in N channel means ND, P channel means NA, sir. right? Where ND or NA you can call ND or NA, nothing but what? Doping concentration of channel. In N channel ND, P channel NA you can call. Confirm, sir? What is that A? A stands for half the width of the channel, students. Half the channel width you can call. Why do you say half the channel width? Means you know that each barrier can occupy maximum only half the width of the channel. So none of the barrier can able to consider complete channel width because the barrier expand from both sides. So each side the barrier can able to take maximum how much width of the channel means half the width of the channel. So A equal to half the channel width you can call. Can we know? And epsilon equal to permittivity of the channel media. Permittivity of channel media you can call. So there epsilon equal to relative permittivity, sir. Suppose silicon you can call around 11.7. Epsilon equal to permittivity of free space. So that the pinch of drain voltage depending mainly on channel width and doping concentrations of the channel. So on these two factors it is depending, sir. Mainly it is depending on two factors, channel width and doping concentration of the channel. Right? It is the minimum drain voltage where the drain current becomes maximum and constant, students. Okay. So next you check out that pinch off region you can call. In pinch off region, what I told you, ID remain constant because already it attains maximum, sir. Right, ID remain constant even VDS drain voltage increases you can call and have a flat response, right? And have a flat response and have a what, sir? Flat response you can call. So in this pinch off region it look like act as an ideal current source, students. Okay, where it look like ideal current source, students. Okay. And one more, students, pinch off region I told that saturation mode. So it is look like a saturation mode of a Bjt. Such that pinch off region is also called as a saturation mode you can call. So pinch off region of a FET is the same as saturation mode of a Bjt. By that it is called as a saturation mode, students. Okay. Pinch off region is similar to saturation mode of a Bjt, sir. By that this is called as a saturation region. Okay. So in this saturation mode, in this pinch off region you can call so FET can be used as an amplifier. FET can be used as amplifier, students. FET can be used as an amplifier. Confirm? So FET can able to act as a voltage amplifier there, and VGS equal to VGS off, that is cutoff gate voltage you can call. Okay, you know that ID equal to 0. Act as off switch. Act as what, sir? Off switch. So on switch, off switch, and amplifier conditions I told you, students. Off switch, on switch, and amplifier conditions I told you. See this one now. The pinch of drain voltage, cutoff gate voltage are same in terms of magnitude. In terms of magnitude, both are look like the same, sir. Because pinch of drain voltage is a positive, cutoff gate voltage is a negative there. So if I come to compare with the magnitudes, both are look like the same, you can call same condition. So modulus of EP equal to modulus of VGS off I told you. Remember now, students? So if I go for output or drain characteristics of FET, this is the thing you can call. So for ordinary values of drain voltage, the characteristic graph have a linear portion. So in this linear region, the drain current increasing linearly with the drain voltage. Why it is happens, sir? So in this region, because already you keep gate voltage constant, so current considered mainly with the drain voltage, and a low voltage region, no barrier effect by the drain potential you can call. So increasing of the drain potential, making that movement of carriers also increasing linearly. So the concerned current increasing linearly. So once you reach a pinch off point, there the drain current become maximum and constant for a given VGS. So in this pinch off region, no further increase in drain current, even the gate voltage is changing. Look like have a flat response and act like a ideal current source, where the FET body can also be act as an amplifier, voltage amplifier it can consider. And this pinch off region is same as saturation mode of a Bjt I can call. So at a cutoff gate voltage, no current conductivity can call act as a off switch. So commonly can define that output resistance in this corresponding pinch off region, students, where it acts as an amplifier. So that resistance you can examine later in the parameters of FET. So understand this, the first characteristic graph I discussed, that is nothing but what sir means output characteristics. And you remember, students, in this linear region, drain current is a function of both gate voltage and drain voltage, students. So with respect to VGS it is decreasing, with respect to VDS it is increasing. So in this linear region you see, students, so drain current increasing with respect to drain voltage but decreasing as reverse bias VGS increases. So ID function of both VGS and VDS, students. Here what I told, ID function of VGS and VDS, students, in that area. If you go for this, if you go for pinch off region, students, nothing but saturation region, there you can examine that with respect to VDS it is already constant. With respect to VDS it is already constant. So as VGS increasing, current comes to decreasing, you can call. So ID is a function of only VGS, students. ID function of VGS. So in the linear region, so ID is a function of both VGS and VDS. In the saturation region, ID function of only VGS. Same thing you may learn in Mosfet also, students. So what are the thing you discuss in FET, that to be repeated again in the Mosfet again. Okay. So in the linear region, ID is a function of what? VGS and VDS. In pinch off or saturation region, ID is a function of what, sir? Only VGS. Understand the students all these things? Okay. So in the next session, we can able to check out what are the transfer characteristics, all that one, and thereby can examine what are the parameters of FET, and then we can able to examine the expression for transconductance. Okay. Understand all these things? Right. Thank you. All the best.